Let me write it down here. So we have the asymptotic solution or the outgoing scattered wave. So we find that's equal to the incoming plane wave plus the spherical wave. This like so. So this quantity F here is the important quantity. So that's the scattering amplitude. Scattering amplitude, and that is given by some constant. Let me not worry about the constant, but the important point is that it is the matrix elements of the scattering potential between the incoming plane wave and the scattered state, the outgoing scattered state. So in the Born approximation, we replace the psi plus here. We replace that with the plane waves. Just like that. So that's a bit like iterating the Lippmann-Schwinger's equation. Yes, you put the solution on the right-hand side, and you will generate terms, first order in V, second order in V, and so on. So the Born approximation is just keeping the first order term. So then we get the Born approximation here. So we get then the scattering amplitude is then given by some constant prime the matrix element. Like this. So that replaces psi plus there. So this is actually just a Fourier transform of the potential. Oops, what am I doing here? Yeah. So this is the Fourier transform of the potential. So then it becomes just minus f1 2 pi h bar squared Fourier transform K prime like this. And since we are considering spherically symmetric potential, this matrix elements, this scattering amplitude, then can be calculated analytically to a certain extent. So that gives us, let's call it VQ here, where Q is the difference between K and minus K prime. So that becomes 4 pi upon Q integral from 0 to infinity times the potential, spherically symmetric potential. I think we were here last time. Okay, I'm just repeating a little bit. Yeah, so we have here. So the condition for the validity of the Born approximation is first first order perturbation theory is then that the scattered wave, which is this one here, so the amplitude of that scattered wave should be much smaller than the incoming plane wave in the region where the potential is non-zero. So I should say this in the potential region. So that's the general condition. And one can make some rough estimate for this. It's quite straightforward. I think that I have this in the notes, also in the textbook. I think you can find that. So let's consider now an example. So one common potential that is used to model a nucleus or an atom is the Yukawa potential. So the Yukawa potential. So that has the form of some constant times some decaying Coulomb potential. Decays exponentially. So we can then calculate the Fourier transform of this potential, so that it's just given by Q. VR. So this can be written as 1 upon 2i QR. So then with the Yukawa potential, this integral can be done analytically. It's just an exponential. So then you get something like for the scattering potential. So it's a function of theta here. So the theta is just the angle between k and k prime here. So that becomes divided by h bar squared. Maybe I should separate this mu squared. So that's the scattering amplitude for the Yukawa potential. Actually, it has an interesting connection to the well-known Rutherford scattering formula. This gives me, yes, let me see, what am I doing here? Okay. Okay, so my notes a bit messy here. Yeah, so the Rutherford scattering cross section is given by and this is a scattering between two nuclei, as you can see, Z and Z prime. 60 K4 sine squared phi 2. So the Q here is equal to K minus K prime. So that is equal to 2K sine phi 2. So this is exactly equal to if we identify that one as V0 upon mu. So that's interesting because Rutherford didn't know anything about quantum mechanics at that time. He just made the measurements of the scattering cross sections of two nuclei. It's correct formula. Well, it's experiment, so it should be correct unless the experiment is wrong. So that is given nicely by this first order Born approximation. Now, one can go further and take into account higher order terms in the perturbation expansion. So then this would correspond to the higher order Born approximation. So basically this is just iterating the Lippmann-Schwinger's equation. So we have pi here plus like that. So the higher order Born approximation is basically obtained by replacing this with the solution. Yes, rewrite it like this. So we replace this with phi plus 1 upon e minus 0 plus eta v psi plus. So that's what we have here. So you can see that you get the first order by replacing phi psi plus with phi, and then you get the higher order term. So you can construct an operator equation for this by multiplying both sides by v here and defining this state to be equal to some operator t acting on the incoming wave phi. So this is the definition of t, and the t operator here is called the t matrix usually. So you can see that we have t here also acting on phi. So now everything is acting on phi. So the left hand side and the right hand side are all acting on phi. So then you get an operator equation for the t, which is given by this. So this is just equivalent to the Lippmann-Schwinger's equation. And then one can iterate. So if we iterate this, then we get v, and then plus v. V and then so on. Yep. So get the expansion in terms of the potential, scattering potential. Now it's not difficult to write down this series, but in practice it's can be very complicated to calculate. So maybe one can go up to second order, but beyond that is usually too complicated to do. Unless you can actually solve this integral equation, see if you can invert it and solve for the t, then that could be equivalent to sum into all orders in the perturbation expansion. Okay. So in the next slide I have here, yeah, so that's the high order Born approximation. Yes, so now we want to consider what is called the optical theorem. So the optical theorem is one of the so-called sum rules, which gives an exact relation between some quantity and usually a sum of other quantities. So in this case, in the case of the scattering theory, one can show that the imaginary part of the forward scattering amplitude, so forward scattering amplitude here means the theta is equal to 0, so both k and k prime are along the same direction, is given by the total what's called the differential cross section, the total differential for cross section. So this is the definition of sigma total. So you integrate over the solid angle, the omega. So this sum rule, or in this case, it's the optical theorem, can be very useful as a kind of check of some. If we have an approximation, then we can use this theorem to see if your approximation is good enough. At least to say if it satisfies the optical theorem, which is exact. So this theorem is exact. Then you have kind of good control of your approximation. So it can be used as a criterion when constructing an approximate theory. So it's useful. So let's try to derive this. Yeah, there are a lot of equations, and so I have to kind of compromise here. Usually I like to write everything down on the whiteboard, but it's going to take a lot of time if I do this. So instead, I think I will just go through the derivations, which are available in the notes, step by step, and we try to explain what we have here. So I want to prove now the optical theorem. So the proof then begins by considering the Lipschitz equation here. So that's the starting point. And then we take the complex conjugate, or rather the Hermitian conjugate. Yes, this is the Hermitian conjugate. So we just flip everything from right to left. And we have to be careful when we do that because we're taking complex conjugate. So then the plus I eta becomes minus I eta. But V and H0 are Hermitian, so they do not change. Yes. So V dagger is equal to V and H0 dagger is of course equal to H0. So we have this one here. And then we multiply everything, both sides, by V acting on psi plus. So then we get psi plus like this. Then we have psi plus. So I multiply both sides by V psi plus and replace the phi with a plane wave, because we are taking a plane wave as our incoming state. And these are just rearranging this equation here. So I put this thing to the left-hand side. So now we want to take the imaginary part of this, because we know that the scattering amplitude is given by, let me put, whether I put the K or the K plus. Yes, don't get confused. K prime, yes. So then it becomes prime V psi plus, like this, some constant here. So we have it on the left hand side here. So that's when we take the imaginary part of this, because that's what we are trying to prove. Imaginary part of the scattering potential is equal to the, or proportional to the total and differential cross section, scattering cross section. So the first term here on the right hand side is real, because V is Hermitian, and we know that the expectation value of Hermitian operator is real. So this is real. But the second term, which is more interesting, consists of two components. There is the real part, if you like. This is an operator, so we shouldn't say it's real or imaginary here. But this operator here, so that part here, can be written in this way here. So I think we did this before. So if we have a function like this, and let me put the minus. Eta. So that is equal to the real part plus I pi delta x. So you can see this by just multiplying both sides with 1 upon, both sides with down. So this is just 1 here. So you see that you get, if you do this, then you get x plus I eta divided by x squared plus eta squared, like this. Yep. So then we understand that eta is a small number, so infinitesimal. So the real part is just 1 upon x, because this goes to 0. And the imaginary part becomes eta upon x squared plus squared like this. And that is a delta function times pi. That's when you take the limit eta goes to 0. So that's why you get this expression here. Okay. So, so then this term gives you a real number when you take the expectation value with respect to the psi loss. And then you end up with the imaginary part, second term. So we do that. So then the imaginary part of this scattering amplitude, so that's proportional to the scattering amplitude, is given by this expression here. So that just comes from what we had earlier in the previous slide. So now we replace that one with our definition of T over there. And phi is a plane wave. So get second line here. So to calculate this matrix elements, as usual, if you have an operator, in this case it is H0 and the T, of course, also, but we don't know what T is. So it's just something that's operator is defined with respect to the scattering potential, so that's arbitrary. But for the H0 part, we can do something. So we introduce then a complete set of states here. This is the momentum eigenstates, which are eigenstates of H0. Yes, they are free particles. So we just insert complete set here. So that's one. If you have to integrate over K prime, of course. And then we should not forget the density of states in K space, which is given by L upon 2 pi to the cube. And so that we are here in the third line here. So now we can operate this operator, delta of E minus H0 on K prime. So then the H0 is replaced by H bar squared K prime squared divided by 2m. It's just that's an eigenstate of H0. So we have this line here. And then we use the spherical coordinates. So we have the radial part and then the angular part. So E is the incoming plane wave energy. So that's h plus squared k squared divided by 2m. Now we can do this in a slightly different way from the one I have in the notes. That's the same thing. So we can use this relation of delta function, so that becomes 1 upon a delta x, and take out the constant here first, and we get squared. Okay. So that is equal to k plus k prime, k minus k prime, like that. Now, k and k prime are positive numbers. So this thing then will be some positive numbers. So it's not 0 unless k prime and k are equal to 0. But we are considering some finite k here. So then this becomes 2m divided by h bar squared. So that becomes, we can take this out, k plus k prime equal to just 2k. So that is equal to 2k. So the reason it becomes 2k is because we have this k minus k prime. So the delta function is 0 unless k is equal to k prime. So I can replace k prime with k. So I get 2k here. So then I have divided by 2k, k minus k prime, like this. Then we can do the integral easily. So this is what I have here. So I have made use of this equation here. Yep. So the integral over k prime can then be done because we have just a delta function here. And the angular part we cannot do is because we don't know what t is. T is a general thing. But we have to then calculate this for k prime equal to k. So the magnitude of k prime must be equal to the magnitude of k. So that's why we need this condition here. So that's what we get for the imaginary part of the scattering amplitude. So if we go further and look at a differential scattering cross-section, the differential scattering cross-section is given by the square of the scattering amplitude, and the scattering amplitude is given by this matrix elements. So we have t here, not v. So then the differential cross-section is given by this expression here. So I just take the square of that. So if we look at the imaginary part of the scattering amplitude, well, then it's just given by the imaginary part of this matrix elements. And we have shown in the previous slide that is given by this thing here. So apart from some constants, yes. So that comes from the previous expression we have. So let me go back a little bit. So it's from here. Yes, this one here. So then we can replace that one with a differential cross-section. And there's a lot of constants here, but they cancel, and you get in the end k divided by 4 pi times total scattering cross section. So this is the total scattering cross section. So that's the proof of the optical theorem. Now, when we have spherically symmetric potential as a scattering potential, then we can take advantage of this. So we can take advantage of the symmetry, and we can analyze the scattering problems in terms of what is called partial waves and phase shifts. Now, it's not clear what is meant by phase shifts here for the moment. But because of the fact that we have a spherically symmetric potential, this means that the problem can be treated for each angular momentum. So we can analyze the scattering state in terms of the angular momentum state, because of the fact that the scattering potential is spherically symmetric. So we'll see how it works out here. Yes. So the spherically symmetric potential implies that the Hamiltonian is invariant under rotation. So that's what we have here. So dr is the rotation operator. And we recall that the generator of rotation is the angular momentum operator. So that then also implies that the Hamiltonian commutes with the angular momentum operator. So that's what we have here. Because of this commutativity, then we can choose the eigenstates of the Hamiltonian to be simultaneous eigenstates of, in this case, we choose Lz and L squared as usual. Yes. Lz and L squared. So then the eigenstates of the Hamiltonian can be labeled by these three quantities: the energy, the angular momentum L, and the Z component M. So I put this in the red box here. We have the state labeled by E, L, M. So they are eigenstates of H, L squared, and Lz. So these are just the angular momentum states. So we are familiar with this, for example, in the case of atoms. We have a hydrogen atoms, simplest example. Then you have the states. Right here, yeah. So if you look at the position representation of these states, then this will be some radial function, which is labeled by L and the energy times the spherical harmonics. So this is exactly what you have when you have say atomic problem, let's say the hydrogen atom. So it's a general result. So if you have a spherically symmetric potential, then your solution can be written in this way: it's a radial function times the y length. So radial function is then the solution to the radial Schrödinger equation. Yeah. So now we want to use free particle solutions as our basis functions to compute the scattering amplitude. So our goal is to write, so let me write it down here. So the goal here is to write the scattering amplitude. So the scattering amplitude is the essential quantity in scattering theory, because that's what tells us how the scattering state looks like. So our goal is to analyze this scattering amplitude in terms of the angular momentum state, or the angular momentum decomposition. So we will show that this can be written. So I'm just writing down the final expressions, so just to give you some idea about what we are heading. Can be written in this way here. So it's a sum over L of that's also the scattering amplitude for each L channel times the Legendre polynomial. So that's the Legendre polynomial. So that's our goal. Our goal is to treat the scattering problems in terms of the angular momentum decomposition. So the advantage of this is that each angular momentum component of the scattering state is kind of independent, so they are not coupled. So you can solve the problem for each of the component. Now, if you have a non-spherical potential, then you can still use the same analysis, but things become a bit more complicated, because the different angular momentum channels then couple to each other. So you do not have an independent equation like this one here for each L. So you will have a couple equations, although you can still use the same kind of analysis, yes, even when the potential is not spherically symmetric. But here we restrict ourselves to spherically symmetric potential, and things become much nicer. So we have then the free particle solution. So the free particle solution, then this radial part is become the spherical Bessel functions. So that's the solution to the radial Schrödinger equations when the potential VR is equal to 0. Yes. So if you put VR here to 0, then this is the spherical Bessel functions, solution to the spherical Bessel functions. And we will use this as our basis to work out this expression here. So that's the reason why we are doing this. So there is this coefficient CL that we have to determine, because we want to make use of this as our basis for calculating the scattering amplitude. See, and another time. Okay, so that's going to be a bit long. So that is actually a good point for breaking the video. So let's have some break here, and then we continue with derivation of this decomposition of the scattering amplitude. So are there any questions?
I have one question about, so you say that you can use the optical theorem to compare your approximation.
Yes.
How does that work? Because it wasn't clear for me.
Well, I mean, you have this formula, and is it this one here? Okay, so the left-hand side and the right-hand side kind of independent. So if you have a theory, you can calculate your scattering amplitude. Like, for example, the first order Born approximation, you can calculate this. You might think about it, and then you can check whether that is equal to the total scattering amplitude. So actually, the first order or Born approximation does not fulfill this condition, but it's still a useful approximation. It's widely used actually in practice.
Okay, yeah, thank you.
Are there any more questions before we have a break? Okay, if not, then we meet again at 1:15. So let's continue with the partial waves expansion. So we have the solutions for the free particle case for each angular momentum component, and that is given by the product of the spherical Bessel's function times the spherical harmonics. And as we said before, we want to compute the scattering potential, so that is not the scattering potential, but the scattering amplitude, and that is given some constant k prime, k, like that. So we will use this free particle solutions to compute these matrix elements here. So we will insert here like this, sum over Lm and integrate over dE. Yeah, so that's is equal to 1 here. We see we also need to know the momentum representation of these free particle solutions for each angular momentum L and M. We know the position representation of the solution, and we have to figure out this coefficient CL. And to do this, we need to know a formula. It's a well-known formula. It's a very useful formula to know this. So if we have a plane wave, we can expand this in terms of the Bessel's functions, the spherical Bessel's functions, and the spherical harmonics. This is an expansion of the plane waves in terms of spherical harmonics and the plane waves. So this sum over M is equal to 2L plus 1 divided by 4 pi. So there's a formula that relates that sum to the Legendre polynomial. So that's why we get the second line here. Okay, so now we will work out the momentum representation of these free particle solutions for each energy L and M. So first we insert this unit Brita here. So that is just 1 and integrate it over R. And so here is where we make use of the expansion of the plane waves, because this is just a plane wave, so that is just e to the minus ik dot r divided by L to the 3/2. Okay, and this one we know, so that is just this one here. So that's equal to R ELM, and we expand the plane waves using the formula we just had in the previous slide. And the only thing we have to be careful about is the sign, because the formula is for plus I k dot r, but here we have minus I k dot r. But that's just meaning that you have to replace that with minus I here. So we can see that this whole thing here is just the plane waves. Yes, and a factor of 1 upon L to the 3/2. Okay. So now we replace this integral, not replace, but write it in terms of the spherical coordinates. So we have a radial integral and an angular integral. So the angular integral can be done because we make use of the orthogonality of the spherical harmonics. So we have two spherical harmonics. So they are orthonormals. There is some normalization constant, but otherwise they are just orthonormal functions. So we can then integrate over the solid angle. If we do that, then it will pick up the L and the M component. Yes, we have a sum over L prime and M prime. So the orthogonality between the spherical harmonics means that it will pick up this one component, Lm. So everything disappears, except then we have this spherical harmonics, which picks up the value of L prime equal to L and M prime equal to M. So we end up here. And then we make use of the closure relations of the spherical Bessel function. There's quite a bit of math here, but it's kind of unavoidable, so we have to just accept this. It's a well-known closure relation, so you can look it up in some math books. I think this is derived from the equation, differential equation for the Bessel's function. You can show this. It's a kind of orthogonality relations between the spherical Bessel's functions. You can see that you have a delta k minus k prime here. So if k is not equal to k prime, then it's 0. So if we do that, we can do this integral here using the closure relation. Then we end up with something proportional to the delta function in k minus k prime times the spherical harmonics. So this coefficient, CL, that you want to determine, is obtained from this relation here. So we define that our states are orthonormal. So if we have two states, E prime, L prime, M prime, and ELM, then these two states are orthonormal. So then it becomes this delta function of E minus E prime. So E is a continuous variable. So we have a delta function, but L and M are discrete. So we have Kronecker delta, L prime and L and M prime and M. So we then calculate this overlap between our two states, E prime, L prime, M prime, and ELM. So again, we insert a complete set of states, angular momentum states here. Don't forget density of states. So that's density of states. And then we just plug in what we derived before for the momentum representation of our partial wave. So this ELM is called the partial wave because it's a partial wave in the angular momentum in that sense. So you get these two delta functions coming from these two quantities. So that can be integrated because they're just delta functions. And again, we make use of the orthogonality of the spherical harmonics. So we get the third line here. So from this definition of our states, so that's we define it to be orthonormal, I mean, then that gives us an expression for the coefficient C. So the C then can be calculated by comparing this to expression here. Gives us the C, the coefficient. So if we use that result, then you get the explicit expression for this partial wave in momentum space and in the position representation. You get rather complicated constants. But it is important to keep track of these constants because we are going to use these states as basis factors, basis functions to calculate the scattering amplitude, to expand or decompose the scattering amplitude in terms of angular momentum. Okay, so that's basis functions. Now we have to go back to the partial wave function here. Yeah. So this is what we are trying to derive. Yes. So we want to calculate the scattering amplitude and decompose it in terms of the angular momentum by using the base vectors, this ELM in the momentum representation. So the next step is then to calculate this thing here. Oops. Okay. So the scattering amplitude is just given by that matrix elements of the T matrix between K prime and K. That's how we defined it earlier. So you should not worry too much about all these constants here. Just focus on that part. So now we're going to insert. So here we see why we need to know this momentum representation of our free particle states. So we insert complete set here. So that's one. And this one also. And of course, we have to sum over L prime M prime and also integrate over E prime. And then we just use our expression for these two states expressed in the momentum representation. So we get this rather tedious expression here. So we get two delta functions, one from this one and another one from that one. So these are the two delta functions. So the two delta functions, of course, can be just integrated because they're just delta functions. But we also have these matrix elements of the T operator or the T matrix between two free particle states, E prime, L prime, M prime, and ELM. So these are angular momentum states, L prime proportional to the angular momentum states. And T is just given as a series of V and so on. So they are just a series of the scattering potentials. And the scattering potential here, we have assumed it to be spherically symmetric. So then this T matrix, so this T operator here, is also spherically symmetric. Yes. So this means if we have something which is spherically symmetric, so that would then correspond to L equal to 0 if you think about it in terms of spherical tensors that we did earlier. So this is spherically symmetric. That corresponds to L equal to 0. So that's like a scalar, because when you rotate, it doesn't change. So that's like a scalar. Yes, L equal to 0. Scalar mirror. So that's tensor of ring 0. So then we can use the Wigner-Eckhart theorem. The Eckhart theorem. So you have this matrix elements, and if we consider this state here, then we see that that state must transform at the rotation according to the L representation, because the T corresponds to L equal to 0. So it's a bit like adding two angular momentum, L equal to 0, and something else, L here. So L0 plus L, well, then you just got 1. Yes. So there's only one possible state. Yep. So you have this, this usual formula. Yes. For the total L. So because L1 is equal to 0 and that is equal to L, then there's only 1. Yes. So that implies that this matrix elements is 0 unless L prime is equal to L and M prime is equal to M. So, and the energy is of course the same because we have elastic scattering. So we have to keep that always in mind. we have elastic scattering. So then we have this result here. Yes. So this is just some number. It depends on the system, of course, that involves some integrals over the radial part of the wave functions. So that's where this TL comes in. So E prime equal to E here. Okay, so now we continue. So so here we have replaced that matrix element here. So we use this expression here in the next slide. So because of the Kronecker delta in LL prime and NM prime, then the sum over L prime and M prime disappear. So we are just left with one sum over LM. And we have this TM, which depends on the system, depends on the potential, scattering potential. So the delta functions can then be just integrated. So that's quite simple. So then that gives us k equal to k prime, because that's the requirement of elastic scattering. And if we do that, then we end up with this result here. And then we can sum over M. So we use that formula that we wrote before. We have a sum over M of psi M and psi M star is then equal to 4 pi or 2L upon 2L plus 1 upon 4 pi, I think, times the Legendre polynomial. So theta is the angle between k and k prime. And then we can just do some redefinition. This TL, so we can just define this quantity FL. And we end up with this expression that we want to show. So you can see that, that the scattering amplitude is now decomposed in terms of its angular momentum component in terms of L. So we notice that there is no dependence on the azimuthal angle, because we are looking at the spherically symmetric potential. So if I have an incoming wave like this, we have a spherically symmetric potential, then the scattering amplitude depends only on the angle theta. Yes, it doesn't matter whether we are rotating around this axis here. We have the same. Yes, so this one and that one have the same scattering amplitude. Depends only on the theta angle. So that is kind of neat expression. So it's very nice. You just have a relatively simple expressions for the scattering amplitude. Now this scattering amplitude can be written in terms of what is called the phase shift. And we will see this later. So before we do that, we want to rewrite the asymptotic solution of the scattering state. In a physically more transparent way. So we have derived before that, that the scattering state is given by this expression here. So we have the incoming plane wave and spherical wave. So f theta here is just the f k. So we know that it depends only on the angle between the two vectors. Now, in the plane waves, asymptotically, if we look at the position r very far away from the origin, then there is the asymptotic form of the Bessel's function. So let me write this down here because I don't have it in the slides. So the spherical Bessel's functions becomes, so this is an asymptotic expansion, becomes a sine L pi upon 2. So again, this is something we just have to accept here. You can find this in the mathematics book. So this can be rewritten as exponential. To I and kr. So this is the asymptotic expansion of spherical Bessel's functions. It's not obvious, but we just have to accept this. So this means that the asymptotic expansion of the plane waves like that. And then this becomes +1. Now make use of the fact that I to the L is equal to exponential I pi L upon 2. So that appears here. Times e to the I kr minus e to the minus I kr minus L pi divided by 2I kr. So I have included, so I have multiplied the I to the L. So that That's why I don't have this face here. And that one becomes L pi because of this I to the L is equal to exponential I p L divided by 2. So if we go back to our expression for the asymptotic scattering state, then we get one PL cos theta. So I'm using this expression that we just wrote down for the plane waves. So that's the plane wave part, this one here. That's the incoming plane wave plus the scattered wave. So we have worked out that that the scattering amplitude can be written in this way here. So I have the spherical wave. Yes, so this is the, so this corresponds to the E dot R. So that's the asymptotic form, and this is the scattered part. So you put things together, then I think we get, can go back now to the result here. So we get that expression. So this expression is actually very interesting. So we see that it consists of two terms for each angular momentum component L. So the interesting thing is that if we look at the case first when there is no scattering potential, so that means that FL is equal to 0, then the scattering state, well, there is no scattering, but anyway, we call it scattering state even when the potential is 0, which is just a plane wave in this case if there is no scattering potential. So in the absence of scattering potential, then the wave function for each L component is composed of two components, two parts. That is an outgoing spherical wave, this one here, and an incoming spherical wave, because you have one plus and one minus. So plus IKR means you have an outgoing spherical wave, and the other one with minus is incoming. But the incoming spherical wave is shifted by this phase L pi. So a plane wave, a free particle solution, can be written or can be decomposed into two components if we look at it in terms of the angular momentum components. There's one spherical wave which is outgoing. This is sum of this outgoing spherical wave and an incoming spherical wave, but shifted by this phase L pi for each L component. So if we look at this expression here, we say that only the outgoing spherical wave is affected by the potential. So this part I think is important, so that it only affects the outgoing spherical wave. So that is because we've been considering the outgoing solution. So if you think about it in terms of time, that would correspond to the retarded solution. So we are looking at a plane wave coming in and then scattered from the scattering potential. So there's an outgoing spherical wave, and only that part is affected. So whereas the incoming part is unaffected by the potential. So now we come to I don't have any more slides here, but I can spend the last 5 or so minutes talking about phase shift. So there is a nice way of formulating the scattering problems in terms of what's called the phase shifts. And we'll see how this comes about. So first of all, we see that we have the amplitude of the outgoing spherical wave is modified by the scattering potential, so that is the FL. But we also know that we have elastic scattering. That's what we have been considering all the time. Scattering. So elastic scattering means that no particles absorb by the potential, or no energy loss or anything. So if I have 10 particles coming in, then we will have 10 particles going out. Yes. So this means that we should have a condition that the incoming flux, so that's the number of particles per unit time per unit area, must be equal to the outgoing flux, because that's what we mean by elastic scattering. No particles absorb. So I want to write this in a more precise way, then that would mean that the divergence of the current density here means particle density, the current particle density is equal to 0. So if we have a volume like this, it means what's coming in here is the same as what's going out. Yes, because that's what divergent means. So if I multiply the divergence by a little volume, well, that's equal to the flux. So that implies that the flux coming in is equal to the flux coming out. So if we look then at the amplitude of the outgoing spherical wave, so the amplitude is given by 1 plus 2ik FL, like this. So this amplitude here, which we call it S, is L, so that's a function of k. It must then have absolute value equal to 1. Yes, it's a complex number. So it's a complex quantity. So that is simply because we cannot reduce the number of particles. So we have an elastic scattering. So the scattering potential can only alter the phase of the incoming wave function. Yes. So this is because the scattering potential can only change the phase, but not the amplitude. So for example, if the amplitude is attenuated, that would imply that the potential somehow absorbs the particle. So we have a conservation of probability. So we have this condition here. So then it's natural to write SL as an exponential like this, because the amplitude is equal to 1, it's a complex number, so we can write it like an exponential of some phase. So this is where the phase coming in. So there's a factor of 2 here, so we'll see later why we introduced 2 here. So we write it like this in terms of some phase. Now, if we do that, we can then rewrite this scattering amplitude okay. So that's just rewriting the F in terms of the S, and now we use our definition of the S in terms of the phase delta L. And so this just after a little algebra you will find that it is equal to okay, so that's quite straightforward, I think. Can also be written as tangent delta L minus IK. So depending on the problem, we will use one of these expressions. Yes. So now we go back to our scattering amplitude. So we can write then everything in terms of this phase. L sine delta L with theta. So this is sometimes called the phase shift analysis. So the scattering problem can be nicely formulated in terms of phase shifts, and we'll see later why we have this phase shifts here. So for the moment, it's just like some phase, but when we consider an example, we will see what is meant by this phase shift. Okay, so I'm already over 12 o'clock. Okay, so maybe we can continue next time. I think we are okay with our time. Yes, so next time we will show that the optical theorem is fulfilled. As it should be, because this is an exact expression. So, but we did it next week then. Okay, so should stop here. So any questions before we quit? If not, then we say goodbye and we meet again on, I think it's on Tuesday next week. So have a nice weekend. Bye bye.